Today on How It's Made. Coconut shell charcoal. Dial indicators. Wet downdraft tables. And bassoon reeds. Coconut shells used to be considered agricultural waste, but today they're processed into biofuel for the barbecue. In countries like Thailand, companies convert the shells into briquettes that burn cleanly for an extended period. Throwing away these shells would be a real waste of energy. Instead of ending up as landfill, coconut shells are being used to fire the grill. Processed into briquettes that burn virtually smoke-free, the shells are now considered a resource instead of garbage. Converting coconut shells to charcoal starts with a partial combustion process. Inside these brick igloo-style kilns, they create a burning environment that allows the shells to be carbonized, but doesn't reduce them to ash. The kilns are partially underground. The surrounding soil helps to seal the fire. This keeps the air levels down for a slow, smoldering burn. A worker bricks up the kiln door, and he seals these bricks with mud instead of cement. This will allow the door to be dismantled later without ruining the bricks, preserving them for reuse in the next burn. From the top, he ignites the fire using soft wax as starter material. Because of the limited air in the kilns, the fire burns out after 20 to 24 hours. A worker takes the door apart and rakes the charred remains of the coconut shells into a basket. They have been converted into a rich charcoal. He heaps the blackened shells into a pile. And under the intense sun, moisture from water used to extinguish any hot spots evaporates. The charcoal dries out and breaks easily. It's now ready to be processed into briquettes. Workers load the charcoal pieces into grinders. This is dirty work, so they protect their faces with scarves and their hands with gloves. Inside the grinding machines, rollers pulverize the charcoal, reducing it to a fine powder. The powder flows into bins below. A worker then transfers the charcoal powder to a mixer. He adds a generous amount of starch made from the root of the cassava tree. Together with water, The starch will bond the charcoal particles together like glue. The mixer whisks it all together like pastry. The consistency is right when the particles form clumps when pressed together. The moistened blend exits the mixer and spills into a bin. This coconut shell charcoal is now ready to be pressed into briquettes. The next worker loads the charcoal into a press. It forces the tacky black powder through a die to press it into a perpetual hexagon with a hole in the center. As the machine extrudes the charcoal, a worker chops it into briquettes that are just over 3 inches in length. These coconut charcoal briquettes have now taken shape, but they're not yet ready for the grill. They're soft and mushy to the touch and crumble easily. To firm them up, they place them in structures with open fires in the center. They close the doors and leave the briquettes to bake over a period of about 24 hours. The heat fuses the charcoal particles together and the briquettes harden. Out of the curing chamber, this briquette is solid to the touch and clean too. It leaves no sooty residue. From coconut shells to barbecue briquettes, it's been quite a transformation. This coconut shell charcoal is now ready to sizzle. In many disciplines, you have to take measurements. Sometimes those measurements are so minute, they're difficult or impossible for the human eye to determine. So a ruler or tape measure can't help. What you need instead is a precision measuring tool called a dial indicator. On this dial indicator, each graduation is 0.001 inches. A full revolution of the hand measures 100,000ths of an inch. To make a key component called the bridge plate, this automated punch press stamps out brass circles, which are about 2 inches in diameter. Workers place each bridge plate into a manual punch press which makes location holes that will correctly position the bridge plate on the next press. This press makes holes for mounting screws, locating pins, as well as for 3 precision jewels, which reduce friction on moving metal components. This lathe begins the process of shaping a stainless steel rod into the dial indicator's main measuring component called the rack. Under a shower of cutting oil, the machine drills and threads a hole on each end for attaching a contact made of plated steel. Next, this milling machine cuts teeth, spaced 25 thousandths of an inch apart. One of the dial indicator's gears runs along these rack teeth to turn the hand that displays the measurement. This computer-guided machine forms an aluminum bar into another key component called the bridge. The bridge has holes for screws and locating pins that align with those in the bridge plate, so that the two can fasten, sandwiching the gears in between. The bridge also has holes for 3 jewels, which workers insert with a punch press. Jewels are donut-shaped synthetic rubies set in a brass ring. They line the holes for the gears and other moving components. The jewel surface is very smooth, so it eases friction on the component. Workers check every jewel under a microscope to make sure it didn't crack when pressed into the hole. The dial indicator's outside case is made of aluminum, shaped by this computer-guided turning and milling machine. Workers spray the case with powdered paint, using an electric charge to draw the particles onto the surface in a thorough, even coat. Then they bake the case in an oven for 20 minutes to make the paint finish ultra-durable. They put the case on a machine that presses in top and bottom steel stems, which will hold the rack in place. They mount a hairspring on the bridge plate. This spring allows the gear to return to its original position after moving the rack upward to take a measurement. They insert what's called a pinion for the large dial hand in the center jeweled hole, and a second gear into the jeweled hole for the small dial hand. Then they attach the bridge. Next, they insert the rack into the case through the stem and screw a contact into each end. Then they install a brass spring-loaded rack guide. It prevents the rack from rotating so that its teeth always face the rack gear. They mate the case with the rest. Then they push in the stem while holding the hand pinion to wind the gear. They install the printed aluminum dial on the bridge plate side and mount the hand for the small dial on a pinion protruding from the top of the gear. They mount the large dial hand onto its pinion. They place the movable dial into a grooved ring called a bezel and snap the bezel onto the case. When you turn the bezel, the dial moves with it. The back of the case is shaped with a lug for mounting the tool to a fixture. The movable dial lets you zero the indicator. You lock in the dial position with this twist bolt. The factory tests every dial indicator with this micrometer head. It pushes in the rack to a specific measurement. Every time the large hand rotates a full revolution, indicating 100,000ths of an inch, the small dial hand clocks one graduation. This test guarantees no tool leaves the factory without delivering made-to-measure accuracy. Cutting or sanding metals and other materials can produce combustible airborne dust or fumes, which can ignite or be inhaled. That's why it's safer to do this work on a wet downdraft table. This machine captures and filters hazardous particles from the workspace. A powerful blower pulls the flammable dust down through the openings of the grid tabletop. Then, a continuous spray of water extinguishes the dust and washes it down into a reservoir at the bottom, where a filter removes it. Because stainless steel doesn't corrode, this computer-guided laser cuts the components that come into contact with water out of stainless steel sheets. Workers pass each part through a wide belt sander to smooth out rough edges left by the cutting. When the part exits the sander, they thoroughly brush off the metal dust. Then they bend the part into the required shape using a computer-guided machine called a press brake. A welder then fuses the parts, constructing the machine in sections. This is the table section that contains the tabletop and the washdown system that processes the combustible dust. Workers clean all the welds with a machine that uses a combination of chemicals and electricity. They brush on a protective coating to make the welds corrosion resistant. Then they wash the unit with soap and water. In the reservoir at the bottom, they install the water inlet filter. When the blower sucks the dust under the tabletop, spray nozzles douse it with water. The dusty water flows down into the reservoir, where this filter traps the dust before a pump sends the water back up to the spray nozzles. To ensure that no water leaks out, a worker caulks this entire section of the machine with marine-grade sealant. On the left side, they mount the housing for the mist eliminator filter. It captures water droplets from the airstream before the blower exhausts it. To that, they attach the blower housing. It has a side opening for the blower and a top opening for a silencer that muffles the noise of the blower exhaust. Now they install the blower. It consists of an electric motor turning a blower wheel. The resulting centrifugal force sucks air through the machine and out the exhaust. They insert the filter into its housing. The filter is polyester, so it's mold resistant, which is critical given that it gets wet. Now they install the water tree, a stainless steel wall with baffles that make the dusty water cascade into the reservoir. These probes ensure there's always the optimum amount of water circulating through the machine. They send an alert to the control panel if the water level in the reservoir rises too high or drops too low. After installing a plumbing connection for the washdown system, they install walls to contain the dust over the work surface and the silencer over the blower exhaust. Then they complete the assembly of the washdown system by connecting pipes with spray nozzles to the plumbing connection. Finally, workers install the tabletop, made up of 2 steel grates. The blower sucks the dust through the grate's openings. You can cushion the tabletop with a rubber grid mat. When you press the start button on the control panel, the blower begins drawing air and the nozzles begin spraying water. This demonstration with the smoke machine shows the powerful downdraft that gives industrial workers a breath of fresh air. To play most woodwind instruments, the musician blows air through a reed made of cane. The reed vibrates to create sound, just like the vocal cords in our throat. A bassoon reed is comprised of 2 thin blades of cane rather than 1, so it's called a double reed. A bassoon reed has twin blades at the top that vibrate to produce sound, and a tube at the bottom that fits onto the bassoon's lead pipe. The reed maker begins with a stalk of cane that's almost an inch in diameter. With a single strike of a cylindrical X-shaped blade, he splits it into 4 equal strips. Then uses a guillotine to cut each strip to a length of 4 3/4 inches. After soaking a strip in water for about 8 hours to soften the fibers, he laterally slices off about half the cane. Then he places it in a precision gouger and thins it to approximately 0.05 inches, give or take a fraction of an inch. He verifies the thickness with a precision measuring tool called a dial indicator. He clamps the cane in a reed-shaped template and trims away the excess. This gives the cane a distinct contour. He removes the outer layer of rigid bark and thins out the middle, which will become the dual blades of the reed. Next, he cuts a pattern that will enable the reed to vibrate at the frequencies required to produce the bassoon's full range of 44 notes. Then he scores both ends of the cane to make them flexible enough to be bent into a half circle. He folds the cane in half and ties it with a piece of brass wire. The fold will form the double blades at the top of the reed. The opposite ends, once bent into mating half circles, will form the tube at the bottom. Keeping the cane wet, he heats a cylindrical forming mandrel over the flame of an oil-burning lamp. Then he wraps the tube end tightly with twine. The heat softens the cane's fibers, molding them under pressure from the tightly wound twine to the shape of the mandrel. This forms the two adjoining half circles into a perfectly round tube. After a few seconds, he removes the forming mandrel and unwraps the twine. He inserts a holding mandrel of the same diameter and wraps it with a rubber band. He puts the reed aside to dry for about a week. This sets the shape permanently. When he unwraps and unfolds the reed, he sands the edges of the two adjoining half circles so that they meet perfectly. Then he refolds the reed, securing it with 3 wires spaced at specific intervals. The distance between the wires, in concert with the curved shape of the cane, finalizes the contour of the reed, which determines how it vibrates. Once the wires are correctly positioned, he wraps the tube end of the reed with strong synthetic string. This will contain the tube dimensions when the reed is re-soaked. He coats the string with glue to further strengthen the tube. Once the glue dries, he reams the inside of the tube to fit perfectly into the bassoon's lead pipe. He places a ruler against the first wire and makes a mark of just over an inch out toward the folded tip. Then he clips off the folded tip. The reed now has double blades that vibrate when the musician blows air through them. Because cane is a plant, not a synthetic material, there are slight natural variations from reed to reed. So bassoonists make the last minor adjustments themselves with profilers and other tools until their reed vibrates beautifully.